So the thing is that you can, so the advantage is that PIXE can be simultaneously performed with other ion beam techniques like Rutherford backscattering, nuclear reaction analysis, particle-induced gamma ray emission, or, for example, scanning transmission ion microscopy. So in one single measurement, beside PIXE, you can do other ion beam techniques. And obtain additional information, which you otherwise you cannot obtain having only with the PIXE technique. So this is, let's say, the basic graph that describe what ion beam analysis is. So from this side, so this is the sample, you have ions hitting your sample. And here, depending on the type of reaction that you have, this will be the basis for different ion beam techniques. So in case your incoming ions are scattered in a backward direction, so they are elastically scattered of these incoming ions, this is the basis for Rutherford backscattering spectrometry. In case your incoming ions result in a nuclear reaction, you can have emission of nuclear products like particles or gamma rays, which is then the basis for nuclear reaction analysis techniques or particle-induced gamma ray emission. Also, in case of thin samples, your ions can pass through the sample and lose their energy. So when you measure the energy loss of incoming ions, you basically perform scanning transmission ion microscopy. And finally, we have this elastic scattering recoil of target nuclei. So basically, you kick out the target nuclei. This is the basis for air depth profiling technique. And today we will focus on PIXE spectroscopy. So we will detect the emission. So we will have the emission of X-rays, which will then detect and obtain some information about our sample. So here, this slide shows some basic steps that are involved in reaction where we have, as a result, emission of X-rays. So you have the ion. So this is one simulation what happens with your proton beam, 2 MeV proton beam in sulfur. So basically, as your protons go through the sample, they react, they are getting scattered, and finally they stop. And here the range of your 2 MeV protons in sulfur is around 50 micrometers. And this is something that we call the stopping power of ions in the material. And we have usually the majority of energy of the beam is deposited near the end of the range. The next step that is crucial for PIXE spectroscopy is the ionization of inertial electrons. That means that your proton will interact with the inertial electron. The electron will be kicked out. And what you will have a hole in this inner shell. So the next step is that this inner shell will be filled by electrons from the upper shells, and they will result either in the emission of X-rays, or this X-rays that is emitted can be absorbed within the atom itself, and it will result in the emission of Auger electron. So in that case, you don't have the emission of X-rays. So this is something that has to be taken into account when performing quantification. And finally, in case of thick samples, if your X-rays produced somewhere in the depth, somewhere in the samples, these X-rays need to reach the surface to be detected. So you have to take into account also the attenuation of X-rays in the sample. So the energy of characteristic X-ray lines, they depend on the energy difference between the levels that were involved in the transition. So K series means that we have a hole in this K shell and it's filled from upper levels. In case we have a hole in the L shells and filled also from the electrons from upper shells, we then talk about L series. And this is what we call what we have is diagram lines. But also we have something, so diagram lines are characteristic X-ray lines, but besides these characteristic X-ray lines, we have something that we call non-diagram lines, which are, let's say, satellites, hypersatellites. And for example, this is one example of what is multiple ionization satellites. So in diagram lines, you have hole in K shell, but in satellites, you don't have additional hole, for example, in L shell. So because you have two holes, not one in K shell, these energy levels will be slightly shifted. So this will be a result in the emission of X-rays, which will have slightly different energy compared to your diagram line. So what is crucial for us are tables like this, where we have a list of energies of characteristic X-ray lines. So this is the basis for element identification in X-ray spectra. So for every element, we have the energy of K series of line, L series of lines, and M series. The crucial thing in spectroscopy is something that we call is X-ray production cross-section, and the intensity of X-ray remission will depend on the probability that the incident ion will ionize an atom. So that means that your ion didn't interact in some other way with nuclear or electrons. And also we have to take into account this probability that photon will leave the atom and not, for example, Auger electron. So when we talk about this X-ray production cross-section, the crucial question is why we use photons in the energy range between 1 and 4 MeV. Well, the thing is that this maximal probability, so this probability that we will ionize inner shell electrons, is related to the incident ion velocity. So if this ion, our proton, has velocity that is similar to the velocity of this bound electron, then you have the highest probability that we will have ionization, that the electron will be kicked out of the atom. So basically, if we want to ionize phosphorus, we need to have the energy of protons of maximum ionization. So maximal probability for ionization will be for proton energies of 2.4 MeVs. So basically, this is a stated X-ray production cross-section as a formula. So we have, this is the K-shale ionization cross-section, and here is this fluorescence yield. So fluorescence yield is this probability that that will result in the emission of X-rays not in Auger electrons. So as you can see here, the ionization cross-section. So this is ionization cross-section plotted versus the energy of protons. So you can see that this ionization cross-section increases with the proton energy, and also it decreases with the Z of elements. So let's say that, for example, if we use 2 MeV protons, we see that the ionization cross-sections are higher for light elements. So that's why we say that the excitation for Pixie is, let's say, more efficient in low Z elements. Contrary, for example, to X-ray fluorescence technique, let's say that which is more efficiently exciting these higher Z elements. Also, here, this X-ray fluorescence yields. So this is the plot versus atomic number, and this is for K shell, for K lines, and this is for L lines. So this means that for low Z elements, majority of this events will result in the emission of electrons. So we will have only small percentage of X-rays lines emitted compared to when you go to the higher Z elements, where majority will be result in the emission of X-ray lines. So when you compare PIXE with other ion beam techniques like ERDA, RBS, for example, you see that the cross sections are rather high. So when we talk about PIXE, we talk about high yield ion beam technique. So this part, I will now cover the experimental setup. So we have, let's say, two basic experimental setup. One is where everything is going on in the vacuum chamber. So here we have the vacuum chamber. This is the entrance of the beam inside the vacuum chamber, where we have the set of collimators. And these collimators are used to define the shape and the size of the beam. Here is the sample holder, and behind the sample holder is a Faraday cup, which in case when we have thin samples, the beam can pass through the sample and it can be collected on a Faraday cup. So we can use this to normalize our measurement to charge. Also, we can put a different type of detectors. For example, we can have one X-ray detector, other X-ray detector. This RBS detector is for detecting the backscattered protons. And for example, we can put additionally gamma ray detector. And here is the inside view of the vacuum chamber. So the beam passes through this collimator. Here is the sample, Faraday cup. And here we have this RBS detector, silicon lithium detector, Sdd detector for X-rays. And usually this type of experimental setups are used for smaller pellets, which can be put inside the vacuum. But in case when we want to measure some big samples, mostly from, let's say, from cultural heritage, then we have this external experimental setup where your sample are placed in air. So you have the beam passing also through collimators, and then here what is crucial, we have the exit foils, which is the barrier between the vacuum part and the in-air part. So your protons will pass through this exit foil, reach the sample, and the emitted X-rays X-rays will be detected with X-ray detector that is also placed in air. So these setups are quite simple to build. You don't have to have additional vacuum pipes, and as you can see, it's very useful for big samples. So here you can see one experimental setup that is at Ruđer Bošković Institute, which is rather simple. So here is the beam with, here is this exit foil, sample, and the detector. But also you can have a more complex system like this, which is at Louvre Museum in Paris, where you have like multiple detectors, helium flow, additional detectors, for example, for RBS, then for positioning and so on. So regarding the detectors, so for what we need regarding the detectors, the goal is to detect the energy of X-rays, and usually we have semiconductor detectors. So when X-rays reach the detector volume, they create electron hole pairs, and the number of these electron hole pairs is proportional to the X-ray energy. So basically, higher energy X-rays will produce much more electron hole pairs, and your signal will be higher. So, and what we can distinguish is the energy dispersive spectroscopy and wavelength dispersive spectroscopy. There are like additional X-ray detectors, but today I will just mention it. I will not go in detail. These are X-ray calorimeters that are based on the fact that you have absorber, and when your X-rays enters this absorber, it raises slightly the temperature of this absorber. So you measure the raise in the temperature, and this raise in the temperature is proportional to the energy of the X-rays, So in energy dispersive system, we usually use silicon-based detectors. The resolution of this type of detectors is around 130 electron volts on 5.9 kV. But you have to take into account that the natural width of K lines is in the range between, for example, 2 and 3 electron volts, or even less. You see that with this you don't have very high, you have moderate energy resolution, but it's good enough to perform PIXE spectroscopy. Typical areas of the detectors in the range between 10 and 80 millimeters, and thicknesses are in the range between 3 and 5 millimeters. The only thing is you have to take into account that you have to have cryostat, because this type of detectors are cooled with liquid nitrogen. The advantage is that this type of detectors, these Sdg detectors, have very high efficiency over large energy range, and it has sufficient energy resolution in most cases. But the disadvantage is that you have to have the liquid nitrogen supply, and also you have the problem that it has low count rates. The next type of detector that are used in energy dispersive systems are silicon drift detectors, or SDDs. They are a little bit thinner compared to the Sdg detectors, and then the big advantage is that they can obtain very high count rates with a good resolution, and also then they don't rely on liquid nitrogen cooling, so they have moderate cooling is sufficient. The problem is that they have small areas, and compared to Sdg detectors, they have lower efficiency at higher energies. And here is the data acquisition. So you have a sample. You have an X-rays reaching your detector, and they produce a rather small signal inside of your detector. So you have to have the system of preamplifier which is very close to your detector. And this preamplifier will, let's say, amplify your signal, and then this signal will go to the amplifier, which the signal will go through additional amplification and the shaping. And finally, you have to convert your signal from analog to digital using analog to digital converters. So basically, at the end, you have your spectrum. So for us, the crucial thing is what we call is detector efficiency. So this is the curve that tells you how your detector behaves with versus energy. So you can see that in this mid ranges, so between, let's say, 1 or 2 kVs, almost up to 20 kVs, you have almost 100% efficient detector, but at edges, your efficiency drops. So this efficiency can be obtained from theoretical predictions, or you can do like direct measurements through standards to obtain this curve. So the lower energy part is mostly determined by the type of the detector window, because this detector window will absorb this lower energy X-rays. And the higher energy part will depend on the thickness of the detectors. For example, in Sdg detector, which are thinner detector, this curve will drop because their efficiency is much lower in this region. So, for example, instead of going like this, in SDDs, it will already drop here around 10 kV. You can influence detector efficiency depending on your type of the sample you want to measure. So here is the comparison of detector efficiency for different type of filters. So for example, if you don't have filter, only window in front of the detector, this is how your detector efficiency looks like. But in case you put like a Mylar filter or a Mylar filter with the hole, you can obtain different efficiency curves. So here is also how it looks in your spectra. So this is the your spectrum obtained with no filter in front of the detector. So you can see also lower Z elements or lower energies of X-rays. But in case you put the filter, this high energy X-rays will pass, will not be absorbed in your filter, but these lower energies will be filtered. So this this fact can be used when you have samples that can have very high count rates, and which will produce some pileups. So you can combine two detectors, so one without filter and one with the filter. So you can get you can have both sensitivity for lower Z elements and for higher Z elements. So, for example, this is the one example of a spectrum detected with Sdd detector, which has low efficiency at high rate. As you can see here in this region, you basically don't detect anything. But this doesn't have a filter in front, so you can see also these lower energy X-rays. But in case you put the filter in front of silicon lithium detector, which has better efficiency at higher energies, you filter out this lower energy X-rays, which produce very huge signal. And then you're more sensitive for this region where you can see trace elements. For example, here are some trace elements not visible with Sdd detector. So here is, as I mentioned, we have two systems. So this is one system is energy dispersive system. We have additional, this is wavelength dispersive systems, which instead of having X-rays detected with detector that are placed very close to the sample and which detect directly the X-rays, in case of wavelength dispersive system, your X-rays are scattered from the crystal and detected with position sensitive detectors. And in this case, the resolution is in the range of 1 and 5 electron volts compared to the energy dispersive system where your resolution is in the range of 130, 150 electron volts. And this is, for example, one experimental chamber where you can see the beam hitting the sample. Here is placed, here we have the crystal and behind is the detector. And for example, this is just to show what this type of detectors can be used. This is mostly for performing chemical speciation studies where you can detect silicon K lines in different compounds, and from this spectra you can determine, for example, what is the type of ligand that is bound to the silicon atom. So here is just the comparison. So this is one spectrum taken with energy dispersive detectors, where in a single spectrum, within 10 minutes, you can detect all the elements in the periodic table and perform quantification. But in case of wavelength dispersive system, you can only see one narrow energy window. For example, this is silicon, and in energy dispersive system, it is seen only as a single peak. But if you measure it with wavelength dispersive system, which are basically high resolution system, you can see that in this line, basically we have a set of different lines. So this is diagram line, and these are all satellites, multiple ionization satellites. So with this method, you detect only 1 to 3 elements, but you can perform chemical speciation, which you cannot perform with PIXE. So this is how the PIXE spectrum looks like. Usually peaks are situated on a background, and which is due to the Bremsstrahlung. Because the electron and ions slow down in the sample and they emit, let's say, continuous electromagnetic radiation that produces this background in the region of lower Z elements. So how we perform identification of elements in the sample? So from this, this is one spectrum, we read out the energy. So we know for these two energies, normally we have to perform the energy calibration in a way that we put some standards, for example, monoelemental standards, and which we know the composition. And after we perform the energy calibration, we can put our unknown sample inside, read the energy, and from these energies, we read in the table, for example, that in this case, we have manganese. So in case of K lines, we will see usually 2 peaks. So this is one is K alpha and K beta line. In this case, for example, you have 3 numbers stated, but this K alpha 1 and K alpha 2 are very close. So they are here in this peak. And usually K alpha line has higher intensity compared to the K beta line. In case of higher Z elements, we detect them through L lines, where we can see the series of several lines. So we also, for each line, we read out the energy, we look in the table to determine what is the element present inside. And in this case, for example, we can determine that we have iodine present in the sample. So we have a series of lines with decreasing intensities as with energy. So some artifacts can appear in the spectrum. These are what we call, for example, in case we have high counting rates, we have peak pileups. That means that detector cannot resolve if, in case when two X-ray photons arrive at the same time, detector cannot resolve it. So it just sums these two X-ray lines, and it creates additional peak, which is usually the sum of this high peak. So for example, you can have these two lines arriving in at the same time. It will produce the signal on the, which is the energy 2 times higher than the original peak. So additional are the escape peaks, which are at the energies of 1.74 keV, lower compared to the main peak, but these are only a few percent. So it's not a high contribution in your spectrum. So regarding quantification, we have to divide, we perform quantification depending on the type of the samples. So in case of thin samples, what we measure is we have the X-ray intensity for specific elements, which will depend on the total fluence, so how many ions hit our sample, the concentration of the element. Also, the crucial is if we have a big detector or small detector, that is detector solid angle, and what we mentioned before, the efficiency of our detector. And finally, this ionization cross-section, so the probability that the ion that will enter inside will result in the emission of X-rays. So in case of thick and intermediate samples, we have to take into account also that our protons lose the energy while passing through the sample. And as you know now, the ionization cross-section are dependent on the energy of ions passing through the sample. So basically, you have to take that also into account. Also, X-rays are, if they are produced somewhere deep in the sample, they are and exit our sample, and they are absorbed in the sample. So we have to take into account this also. But this absorption will depend of the composition of the sample. So it's not quite easy to obtain quantification in case of thick samples, but the solution is to produce some iterative procedure where you can normalize to 100%. So in several steps, you first determine the concentration, calculate the absorption, then again fit the spectra, obtain new concentration, and then again calculate absorption. So basically in this iterative procedure, you can obtain you can perform quantification. And also, since the PIXE can be combined with other ion beam techniques, for example, from RBS, you can determine the matrix composition. For example, you can see light elements that are not visible with the PIXE, and from that you can obtain what is the composition of the sample, from which you then determine what is the atomation of X-rays. So also alternatives are using standards, and from these standards you first perform the measure standards, obtain some parameters, and then use these same parameters to calculate concentration in your samples, which it is advisable that the standards are as similar as possible to your samples. So also you should take care about what is thin sample in PIXE, because, for example, it is not the same to treat, for example, aluminum K lines which have energy of 1.4 keV, or, for example, using some higher energy X-rays around, for example, 10 keV, because, for example, in an aluminum K lines will be already absorbed in a few micrometers compared to the higher energy, which will treat these few micrometers as a thin sample and pass without any absorption. So here is the software that we use for PIXE. We talk about, we mainly use GoPIXE or GPIXE. In case GeoPIXE also enables to quantify each pixel in the maps. So you can obtain the maps and perform quantification on a pixel level. So finally, I will just describe the comparison to other similar X-ray emissions techniques. For example, in case of electron probe microanalysis, usually electrons penetrate only around 1 micrometer below the surface, compared to, for example, as you saw, we have 2 MeV protons reaching up to 50 micrometers, for example, around 50 micrometers. And also the problem which they face in electron microscopes are that you have here very high background. So your PIXE will be situated on a much higher background to compare to one that you have in PIXE. Very basically here in this region you don't have background at all. So detection limits in case of electron microprobes are 1 part per 1,000. Also, another similar technique very often used is Xlr X-Ray Fluorescence, and compared the penetration depth are quite large in the range of millimeters. Also, you have a lot of handheld devices which you can take with you and measure somewhere outside. You don't have to be necessary to be in the lab. And also, in case, for example, if you have synchrotrons, you have the option of tunability of the excitation source. So that means, for example, in case you excite, for example, with 14 kV beam, for example, in this case, you will have so this is one sediment sample which has very huge calcium. And here is the signal of sulfur which you want to detect. By tuning your beam in a way that you have the beam around 3 kV. With 3 kV beam, you will not excite calcium, but you will excite the sulfur. So in this case, for example, the signal in the first case with 14 kV beam, you will have the signal from both calcium and sulfur, but in this case you will have only pure signal from sulfur. So in this way you can optimize your system, and also in some cases on the synchrotrons you can even also focus the beam to microscopic levels. And finally, here is the comparisons also with XRF. As you can see, also XRF has higher background in this region compared to the PIXE, while PIXE has a higher background in this low Z region. But in case of PIXE, detection limits are 1 part per billion, just because you have very low background here. Also, we can obtain a microbeam. And the great advantage of PIXE is that you can use RBS simultaneously with PIXE, which to obtain the matrix composition, from which you can more precisely determine concentration of the elements inside of the sample. So I think this would be a good time, for example, to make a break with and start with the movie. In this section of the movie, you will demonstrate the PIXE experiment. So you will see the selection of the samples and mounting of the samples in the vacuum chamber. There will be a short description of the accelerator and the scattering chamber, and then you can see the acquisition of PIXE spectra for thin standards and unknown samples. So I would ask if the organizers, I will stop sharing. So I will ask if the organizer can just start the movie.
Yes, Eva, there are 2 questions in the chat for you. Maybe
okay, sorry,
to,
yeah, sorry. Yeah. Let me just see, I didn't see it. Wait. So basically, in case of pileups, you look if, for example, usually pileup is real. So the question is how one can define and assign the PIXE pileup. So usually you can observe what is the highest intensity peak in your spectrum, and usually because this peak will have the highest count rate. And in that case, you have to find its energy multiplied by 2 and see if you have on this energy if you have some peaks. So in that case, you will have the pileup. And usually you can distinguish it from basically if you, for example, you have K lines of some element in that region, usually you will miss some peak because, you know, for K alpha and K beta, you have some, you have specific energies. But in pileups, for example, one peak of pileup will overlap with one peak, but will not overlap with another peak. So I can maybe just fastly show you in the presentation. So here is, for example, this peak is the sum twice this peak. This peak will be a signal from K alpha plus K beta, and this will be double of K beta. So you will have, let's say, these three peaks, and usually if you have some elements inside, you will maybe it will overlap with this peak, but K beta, for example, the element will be in somewhere outside. So this is, for example, how you can distinguish you can detect if you have a pileup. So wait, sorry. Okay, I just need to find the chat. Stop sharing. Okay, and wait. So there is a question: in case of absorption detectors, how you determine intensity counts of each peak in a spectrum? I mean, basically we have this efficiency curves. So we usually use standards to see how and to plot this efficiency curve. This is versus the energy. So basically, in that way, determine what is the absorption of specific X-rays in our system. But this is usually problematic for these lower Z elements, for example, below 3 keV. Normally, it depends on the type of the filter that you put in front of the detector. I hope this was the question. I didn't quite understand. Okay, and I think this is the last question. Can you please once more explain about satellite and hypersatellite peaks and what sort of information one can get out of it? Okay, I will start again the presentation. So satellites. So let me start. Okay, I can find it. Okay, I lost the screen. Okay. Wait. Okay, I don't know if I'm sharing correct. I don't know, you can see the presentation, I hope. I don't know if I shared the correct screen.
Yeah, we can see, but we can see the double screen.
Okay, I'm sorry, I'm not very skilled with this sharing. I think maybe this, I think now it's okay. So I will go to this satellites and hypersatellites, sorry. So the thing is that the diagram line is usually transition when we have only single hole in this, so we have one hole in one shell. So you have hole, for example, only here. And then you have the transition where, for example, this electron from L shell will go to K shell, and you have the emission of X-ray lines. In case when your ion kicks out this electron out, but also kicks 1, 2, or 3 electrons, all these energy levels will not be at the same distance. So this energy difference between this K shell and L shell will change, as you can see, for example, here. So these are the energy levels when you have only one hole in, for example, in K shell. But in case when you have additional holes, they will change. So you will have so the final energy difference between this and this level, which is involved in transition, will be different. For example, and that you will see in a way that your line will be shown on some higher energy, and will be, for example, of you will have additional lines. So I hope. I think I hope it's okay, the explanation. Okay, let me just see if I don't know if there are any more.
Now, Eva, excuse me, can I ask you something directly?
Okay.
Okay, so in terms of this filter for low energy, now when you showed this spectrum, we still see the low energy spectrum.
Yeah, because they part.
Why don't you cut it off completely?
Because the problem is then that you start to count. I mean, you see parts, but you have to cut it in a way. You don't have to cut it completely, because, for example, in this case, the problem is that here you are interested, for example, in trace elements, and these peaks, for example, are very high. And then what will happen? These peaks will produce you pile up in this region.
Okay.
So basically, you will have these artificial peaks that are not your element and will create you problems. So what you want to do with the filter is just that you cut it slightly, so that they don't produce the pileups, so that you have like a more clear image in this region.
Okay, so you just want to clean up the spectrum.
Yeah, we want to clean up the spectra so that we don't have these pileups in this region, and we can clearly detect, for example, trace elements. So for us, it's not crucial to cut it completely, because otherwise you will start to absorb also these maybe that are out of your, I don't know, you're interested maybe in these peaks also, but if you put too thick filter, you will cut also this part. So
okay, and one other question, is there the lower limit of thickness? So because of the signal, so probably you have the preamplifier and the electronics that produces the signal in the end, but when you say thin targets, is there a limit of what is the thinnest target you can actually analyze?
I mean, so far we didn't have. I mean, mostly you cannot go. I mean, you can have it as thin as possible as long as you have some signal from it. But so far, I don't think we ever had problems. I mean, to measure. I mean, only the problem is that you have, for example, extremely low concentration in very thin samples. For example, you want to detect some impurities in thin samples, then you have like problem. I mean, then if you want to really have low concentration in very thin samples, then it can be a problem.
Okay, maybe then when we have the experiment, the practical, I will ask you more questions about
I mean, in this section we will not have practical. I will just show you examples. So
but this will, I think it will be on Monday or Tuesday. I don't remember.
I don't know. Regarding Pixie, I don't think, no. we don't have scheduled it. So
okay, never mind. Then maybe in private communication.
Yeah, I mean, you can send me an email. It's not a problem. So.
Thank you.
Yeah, no problem. So if in case there are no questions, I think we can start with the movie.
Excuse me, just one question regarding this satellite again. So like you are explaining that these satellite peaks are corresponding to the whole, and every peaks have some sort of a delta shift.
Yeah, they usually have. If you have additional holes, they have a they shift. So you have this energy difference is not the same as the energy difference here in diagram lines. So they will not be at the same position in your spectra. I mean, I will show you here on this spectra. You can see it I will do it very fastly. So this is this. Wait, sorry. I will reach it at one point. Sorry, here. So this is this. For example, this is the diagram line. And this is also diagram line. So K alpha and K beta transition. And this is the peaks that are, this is peak that has additional hole in L shell. So the same transition as this, but this has only hole in the K shell, and this has additional hole in L shell. And here, this peak has two additional holes in L shell. So these are these peaks, these satellites.
Okay, so that means from the satellite peak, one can detect some sort of defect states.
I mean, basically, we use it for chemical speciation studies.
Chemical specification. Okay.
Hi, Eva. May I ask you a question?
Okay.
Could we be able to track cadmium and selenium in quantum dots labeled microplastics?
I mean, we see, yeah, I mean, cadmium, depending on the concentration of this cadmium inside, I think, I mean, cadmium we can see through L lines, I think they're around 3 keV. For selenium, they're a little bit on higher, they have a peak above, I think, around 10 keV maybe, so, but it depends on the, I mean, in PIXE Spectra, we can see cadmium and selenium, but it depends on the concentration, so.
Okay, and what do you need to, as a sample holder, in order to be able to send you and try if we could track it? Because I have.
Okay, but is it okay? I will put in my presentation at the end my email, so maybe it would be easier if you can send me an email so we can discuss.
Yeah, thank you.
Yeah. No problem, no problem. Okay, so I think maybe we can start. Start
I
with the
share,
movie.
yeah,
Okay, thank you. Thank you.
Just a second.
No problem.
Yeah, just a second, because one issue, just a second.
Hello, I'm Matea.
And I'm Eva.
Can you please confirm if you can see and hear the video?
We are in the laboratory for ion beam interactions at Ruđer Bošković Institute, Zagreb. And now we will demonstrate the PIXE experiment.
The main task of today's experiment is to demonstrate the process of Pixie measurement in determination of elemental composition in solid samples. For this experiment, we'll be using a set of certified reference materials and standards in order to calibrate our detection system and then verify the calibration performed. So here we have prepared a set of single element calibration standards, either single element or simple compounds of these elements that are deposited on a stable solid backing, which is a Mylar or nucleopore filter. For the verification of the calibration, we have prepared a multi-elemental certified reference material, also deposited on a thin filter. The calibration and verification process will only be done for the thin samples in order to avoid any problems that may arise during the measurement from the possible unknown absorption of the emitted X-rays. So after this process has been completed, we will measure a set of thin samples of unknown composition, which will also be air particulate matter deposited on stable solid backing, which is again filter. We have chosen these samples as a demonstration of the application of Pixie in environmental monitoring programs or environmental studies. And in the final stage, we will perform measurements of two thick glass samples, one certified reference material, and one unknown sample, glass sample, as demonstration of application of Pixie measurement in, for example, forensic studies or cultural heritage applications.
So behind me is the accelerator system. Everything starts with the ion source, where negative hydrogen ions are produced. Negative ions are attracted by the positive potential of the accelerator. At the moment, we have 1 million volts at the terminal of the accelerator, which will result in the total energy of 2 mega-electron volts for protons. The beam will be transferred through the sets of magnets into the experimental chamber.
So right now we're in front of the Pixie chamber, which we will open to let to put the samples inside.
The beam is entering the chamber through the set of collimators that define the shape and the size of the beam. The beam hits the sample, but in some cases it can pass through the sample and enter Faraday cup. Faraday cup and the sample holder are electrically connected, so we can measure the total current during the experiment. Around the sample holder, we have a wire with negative voltage applied that prevents emission of the secondary electrons. On the left side, under 45 degrees, we have a silicon lithium X-ray detector. This is a large area detector with a filter optimized for detection of higher energy X-rays. Below the exit tube, we have another X-ray detector at 30 degrees, optimized for detection of lower energy X-rays. In front of the detector, we have a collimator and magnet. Magnet is used to deflect backscattered protons, which can degrade the performance of the detector. RBS is also placed in the chamber under 165 degrees. Each of the 3 detectors we are using have their own set of pulse processing electronics, which consists of bias power supply, preamplifiers, and amplifier. Signals from the amplifiers are sent to analog to digital converters, which are connected to the acquisition system. After we mounted the sample inside the chamber, we will close the chamber and start the vacuum pump to achieve the vacuum inside. Now we are passing the beam inside the chamber. First, we need to position the fluorescence screen to obtain the position and the size of the beam. We need to adjust the beam current to 2 nanoamperes because we are using certified reference materials that are very sensitive and can be destroyed with high density currents.
So as we have demonstrated earlier, the chamber is equipped with motors that are connected to our sample holder. And in this way, we can easily manipulate the samples within the chamber. And right now, I will reposition our holder to a calibration standard for which we will collect the first PIXE spectra. Now we will collect two PIXE spectra coming from our two detectors in the chamber. Here on the left-hand side, you can see the window corresponding to the spectrum coming from the Sdg detector, which is optimized for lower energy X-ray detection. And on the right-hand side, we will collect the PIXE spectrum coming from the Sdg detector, optimized for detection of X-rays in the higher energy range. So after positioning the sample into the beam spot, we can release the beam in the chamber and start our acquisition. Okay. So here are two PIXE spectra for a calibration standard, which is composed of nickel deposited on a thin Mylar filter. And in the X-ray spectrum coming from the Sdg detector, you can see two K lines, K alpha and K beta from nickel, and also one L line from the same element, nickel. On the Sdg detector, we can see these two K lines, K alpha and K beta, but the L line on this detector is filtered out because it has 300 micron thick filter put on top of the detector. On both of these spectra, we can see some impurities being present in the sample. For example, calcium. Here you can see K alpha and K beta lines of calcium here on Sdg detector, which actually come from the sample backing from the Mylar filter as an impurity. So the spectra are accumulated until 1 microcoulomb charge has passed through the sample, and then we stop the acquisition. After that, each K alpha line of the measured element needs to be fitted to determine peak areas for the calibration curve creation. So we determine our range of interest and fit. So in case of nickel standard on Sdg detector, this area of K alpha line equals to 56,500 counts approximately. So the data that we collected after measurement of each standard will give us the X-ray emission intensities for each element. And with this data, we will create a calibration curve. With this curve, we will determine the efficiency of our detection system, which will enable us to subsequently quantify elements present in unknown thin samples. After we have measured the whole set of our calibration standards, we are now moving to our real samples of unknown composition. So right now I will start the measurement. Again, here on the left-hand side, we're collecting the spectrum from Sdg detector, and here from Sdg detector. Okay, on a first glance. Let's see what's inside. So here we have on Sdg detector peaks corresponding to K lines of silicon, aluminum, magnesium, little peak, probably sodium. Okay, here K line of potassium, calcium, K alpha line, K beta, and iron. And on Sdg detector, we do this. Okay. Calcium line, probably titanium. Yes. And K alpha, K beta line of iron. Zinc, K line of zinc, K alpha, K beta. Okay, and now we'll let the spectra collect until 1 microcoulomb charge has been deposited in the sample.
So after we measure thin samples, we will measure two thick samples, one reference glass sample and one sample of unknown composition. For that purpose, we had to reduce the beam current because of the higher count rate. So here we can see the collection of two PIXE spectrum from SCILI and Sdg Detector. In case of thick samples, quantification is not so simple as in case of thin samples, because we have to take into account also the attenuation of X-rays within the sample. For that purpose, it is good also to collect the RBS spectra, which is crucial for determination of matrix composition, from which we can then calculate the attenuation of X-rays in the sample.
Today, we have demonstrated the basics of a Pixie experiment.
And thank you for your attention. Okay, I can now start with the rest of the presentation. Let me just share my screen. This one, okay. Okay, so in the this last part, I will show you some. Sorry. I will show you several examples. So I will have one example regarding the soil analysis and a similar procedure for the analysis of air particulate matter. And then three examples of the analysis in the samples from cultural heritage. And finally, just a brief one example of high resolution PIXE experiment. So regarding the soil analysis, we had a very good example where here in Croatia, in Plomin, exists a coal-fired power plant, which in the period between 1970s and 2000 used very super high organic sulfur. So this Russia coal they used had the concentration of sulfur in this Russia coal was around 14%. And the percentage, it had a very high percentage of organic sulfur inside. So we took samples, so here is the power plant, the samples around, soil samples around the power plant. The goal was to determine the major, minor, and trace elements in soil to see if use of this Russia coal caused some consequences for the pollution of the soil in the surrounding area. So we used the chamber that you saw now in the movie. So basically we use the RBS to detect the backscattered protons and silicon lithium with filter for optimized for detection of trace elements and SDD for major elements. So in the procedure, first, this is an example of one backscattered proton spectrum. And basically fitting this spectrum gives you the concentration of major elements, light elements that we don't see usually in PIXE spectrum. For example, elements below sodium, because they are absorbed in the detector window, we cannot see. So this RBS gives us information about carbon, oxygen, nitrogen, and from this and some major elements. And we determine the matrix composition, which is very crucial for this attenuation of X-rays in the sample, because from that we already know what is the what are the major elements in the sample. Then we observe the Sdg detector. So this is the spectra of Pixie detector that is optimized for lower energy X-rays. As you can see here, you can see all the light elements like sodium, magnesium, aluminum, silicon, and sulfur, which is the focus of this study. And then potassium, calcium, titanium, chromium, magnesium, and iron. But this part you see here, we don't see basically because the efficiency of this Sd detector is very low in this region because the detector is rather thin. So from this spectra, we quantify the sulfur and lower Z elements. And then we observe the spectra from the other detector that has filter in front. So as you can see, all these lower Z elements are filtered. So basically, the highest signal is from iron. So for example, here, if you compare, the iron is not so high. So the highest is aluminum silicon, so with Sd detector. But with this detector, these low Z elements are all filtered. And then you have like more sensitivity for these trace elements. And for example, you see zinc, lead, strontium, zirconium. So basically, this detector was then used to quantify trace elements. And the conclusion from these measurements was that the soil, so here is the power plant, the soil is very severely polluted with sulfur, which is a result of 3 decades use of high sulfur Russian coal. And also it was noticed with that you have moderate levels of selenium and cadmium. Okay, so similar studies can be performed also on air particulate matter. So you can collect, collect air on these filters. And in the case of analysis, these filters with air particulate matter are treated as thin samples. And then basically you trace it over a long period, and using the, for example, principal components, you can try to determine the source of the pollution from large data sets. The next example is the example of analysis of ancient bronze statue of an athlete. This statue was discovered in 1996 in the Adriatic Sea here near island Malivoši. And it was raised from seabed in 1999, and immediately restoration and conservation process started, and it lasted until 2005. And also during that period, numerous studies were performed on this statue to determine its origin. So one of the first studies was performed with the portable XRF and external beam PIXE. So portable XRF was performed on 70 samples taken from different areas of the statue. And also external beam PIXE analysis was performed on several spots along on the head of the statue. We used the MeV proton beam, and this beam spot was around 1 millimeter in size. I just wanted to mention that also the dating, there was some organic materials was found inside the body, so the radiocarbon dating was performed on this organic material so they concluded that the statue is probably between 100 BC and 150 AD. And the conclusion from this portable XRF and external beam PIXE analysis showed that basically, there were very high variation of alloy components on the surface between different samples. So copper ranged between 40 and 85%, while lead was in 5 and 50%. So this was conclusion basically that this type of analysis is not suitable to determine the lead concentration in bronze, because basically you analyze the surface, which was for a very long period exposed to seawater. That's why the bronze deteriorated with time. So what we got was cross sections, small cross sections, which, so for example, here was the surface of the sample. Here is the bulk. And what we performed the micropixel analysis with 2 MeV protons and the beam spot of 1 micrometer. So basically we scanned these regions to see how, from the elemental maps, to see how lead, copper, and tin behaves going from the surface to the bulk region of the sample. And what we see basically that the lead concentration dropped as we go from the surface to the interior. And we see basically that this drop is within, let's say, 600 micrometers in the sample. So basically, with the external beam PIXE, we were analyzing this surface region, but the real representative of the bronze was should be from this bulk region. And this was just because this deterioration of the statue, since it was in the seawater for centuries. So the real concentration obtained were like that lead was within 8 and 30%, copper between 76 and 85%, and tin between 8 and 10%. Beside this micropixel analysis, additional analysis were performed like lead isotope analysis, and the conclusion was that the probable origin of the lead was from Sardinia or Eastern Alps, and this is basically the Roman copy of a Greek statue. And that this statue is probably casted somewhere in the vicinity of North Adriatic, where it was originally found. Okay, so the next sample is one object belonging, it's a silver tray, belonging to a collection of very luxury silver dishes. And it originates from late Roman period. These luxury silver dishes were found in near town Vinkovci in Croatia in 2020. And this one sample was just one sample in the series of different samples we received, like bowls, plates, trays from this collection. The goal was to determine the elemental composition of materials, which is needed to know how to proceed with the restoration and conservation procedure, and to gain some insight how these silver dishes was manufactured. So what we used in this case, we used external beam setup because this was too big to put it inside the vacuum chamber. In our setup, we have the possibility that we have a motorized stage, so it is possible to move the sample while beam is fixed in a way to obtain elemental composition, elemental distribution along the sample. We used 2 MeV protons with the spot size of 1 millimeter. And here you can see these are the elemental maps that we obtained. So we scanned the small region of a rider and a horse. And here, basically, you can see that this is the elemental map of the gold and mercury. So you can see that the gold is in the place where we have the horse and the rider's head. Also, here is the silver elemental map. So you have the silver from the plate itself. Also, there is sulfur, elevated levels of sulfur were found in the position of the shield. And also silicon, chloride, and calcium are mainly localized in the engraved areas, which is the consequence of impurities, because this dish was for a long period buried in the ground. And here you can, for example, see the composite, RGB composite map, where, for example, sulfur is represented with red color, gold with green, and silver with blue. What we performed, the multivariate analysis of these PIXE spectral images, because we wanted to determine elemental composition and eventually find some additional information. And what we found, for example, that these all blue regions are regions with where gold is present. And here, basically, you can see how, because you have gold and mercury lines, you see in the spectra, because we have a thin layer of gold, and below is the silver plate. So from the taking into account that we have a thin layer of gold, we have silver X-rays passing through this gold layer and being absorbed. So this conclusion made possible to perform the analysis of the thickness of this gold layer, because taking into account that, for example, the regions where you have the dark blue are the thickest region, and here you have the highest intensity of gold, but the intensity of silver, since they are absorbed in gold layer, but not completely, are low. But as you go to the surrounding neighboring, so the edge areas, you have much thinner gold layer. And in that case, so this is like light blue, in this case, silver lines are much higher because they are not so absorbed, substantially absorbed. And this made it possible to determine the concentration of the gold and mercury in these layers and to find the layer thickness. And then the final example from the cultural heritage is the pigment identification. So we had one illumination from 15th century book of poems by the Roman poet that was given to us, so borrowed from National and University Library in Zagreb. The goal was to identify pigments used for illumination and to understand the materials and decorating technique, and of course for conservation purposes. So we used the same experimental setup as in the previous example with 2 MeV protons and spot size of 1 millimeters. And we also performed the scanning of the sample around the area of the flower. So here you can see also the elemental distribution of silicon, calcium, barium, iron, copper, zinc, gold, mercury, and lead. So from these elemental maps, you can see, for example, that in the area of yellow dots, it is related to gold and mercury. So basically, in this case, gold leaves were used for these areas. For blue and green pigment, it is associated with the copper map. So it is some type of copper-based pigment. And finally, we have lead, which is related to the red pigment. In this case, with all single pixel technique, we were not able to determine whether this is minium pigment or some organic pigment that is mixed with lead white. So in this case, some additional measurements should be performed with some other technique to distinguish what is the real this red pigment. So for this is just preliminary information, but if you perform a multivariate analysis on this image, you can also obtain spectra from cumulative spectra from red, blue, green, and yellow regions. And here in the spectra, you can identify all the elements that are present in the individual pigment. And of course, in this case, it's rather difficult to perform quantitative analysis, but some semi-quantitative analysis can be performed related to determining the relative concentration of trace elements to copper. But in this case, we identified that the blue pigment is azurite. For example, red can be minium disorganic pigment, which we cannot determine, and this is the gold leads. And for green, we were also not sure because there are like several copper-based green pigments, so we were not sure about the green pigment. And finally, this is the example of one high-resolution PIXE experiment. So basically, this is a high-resolution experimental chamber where you can obtain the very narrow PIXE spectrum, but with very good resolution of a few electron volts. And the purpose of this study was that on Mars, they use alpha particle X-ray spectrometers. So to determine the elemental composition of rocks, they excite the samples, the rocks, with alpha particles. And usually they have a problem. They don't have a good database of spectra collected with helium particles. So we were given a task to determine how the spectra, how these satellites behave when we excite the samples like magnesium or magnesium oxide with helium particles. So we investigate how the spectrum looks. So basically, as I mentioned there with protons, this is the diagram line, and everything is satellite line. So it is substantially different compared to the PIXE spectra, where you have this diagram very high, and this satellite region has a very low contribution. But in case where you excite your sample with helium, your spectra, high resolution spectra, looks quite different. And this is what caused the problem also in energy dispersive spectra, and it had the problem for quantifying the low Z elements from spectra that were collected on Mars. So based on this request, we measured the influence of different energies of helium on magnesium oxide, aluminum and its oxide, and we covered all the elements up to calcium, which is now used to parameterize the helium-induced X-ray spectra, from which they created the database to perform quantitative analysis of spectra taken from Mars. So basically, this is it. Here I listed some of the references if somebody is interested to learn more about PIXE. Also, this is some instrumentation and documents that you can download from the EIA webpage, and links to the software, which are not free, you have to pay. And this is basically it. In case you want to discuss in more details regarding some measurements, I put my contact here. So you can send me an email and we can discuss if something is possible, or we can measure some samples that you have. So I want to thank you for your attention. So in case somebody has some questions, I can reply.